and pretty much all the necessary skills you need, and that pretty much covers everything you would need for solving, in particular, solving vibration-related dynamics. Okay, so that means second-order differential equations with initial conditions and subject to some common force. Here, I can demonstrate another example. So we can demonstrate another example here with. Right now, I'm still working on the designing of the next homework, and that homework will be similar to this one. So I will give you the certain dynamics, say x double dot plus 4x dot plus 3x, okay? And so that means the m equal to 1, c equal to 4, k equal to 3, something like this one. And this one, I say, is equal to e to the t. So that is a very weird force excitation. But that's for exercise, I simply adopt this one. And in addition to the external excitations, this system also have the initial conditions. So we want to determine the total response. Okay. You might be able to solve for these problems, and by using mathematical traditional approach, you decompose these total solutions into the transient solutions, and also calculate the steady-state solutions. Okay, then composition of the two will be the answers. And this one will be very tedious, but you can give it a try. I would recommend is to use the Laplace transform, because this method actually is very quick. Okay, if you get familiar with this approach, that saves you a lot of time. So here are the solutions I want to demonstrate using MATLAB. The Laplace transform. So we take the Laplace transform on the both side. So that means the Laplace transform of x double dot plus 4 and x dot and plus 3. And the Laplace transform of the ET. Okay? And so here, for these terms here, this one is equal to, we look at the table here, so probably you can use the derivative. So this one is the derivative here. We use this one. So that one is equal to s squared times capital S and minus S times initial conditions and minus x dot 0. Okay? So the dot will be equal to x and minus x0. And the plus x is simply defined by the capital of S. Okay, so that is the notations here. And introducing the whole terms here, and x0 equal to 0, so this is 0, and initial velocity equal to 2. Okay, so we just put the numbers here. So we put everything here, then, and also these terms, e to the 80. E to the 80 is this one. Okay, so 1 divided by s minus 1. So therefore, we arrange everything together carefully. That becomes s squared, capital X, and minus 2, plus 4, and sx, and plus 3x, equal to s minus 1. Okay, so here I have introduced the initial conditions and put into place. And the capital X is the, I drop of the X, okay, so that means capital X, s squared plus 4s plus that will be equal to 1 minus 1 and plus 2. Okay? You good? Okay. So if you, at this moment, if you still remember at the beginning of our class, and at the beginning we learned how to solve for very fundamental, the transient response. And one approach I show you is we start with the characteristic equations. Right? For this one, it is characteristic equations. If you still remember, that is, I told you, is this. You pick up the coefficients of each term, and that characteristic equation is corresponding is p squared plus 4p plus 3 equal to 0. Or you change the variables, something like s squared plus 4s plus 3 equal to 0, right? This one basically is this term here. Okay, so this is another description or explanations of the characteristic equations, and that can be derived from the form here. And by here we don't need to spend time, and that can be explained further in control. And I'm kind of offering control next semester. So if you're interested, you can take it. Okay. Anyhow, that is the one here. So once we have this one, then this one we can further derive, and that becomes s minus 1 and s plus 1 here. Okay. Would that be good? No. 2s minus 1. Yeah. Right? Right? Okay. So in this way, we can have this one, 2s minus 1 and s squared plus 4s plus 3 and s minus 1. Okay. And this term can be factorized as s plus 1 and s plus 3. Okay. So this term is equivalent to this, and keep writing s minus 1 and 2s minus 3. You good? Okay, and then the remaining, we simply factorize the whole things. So right now we have everything here, and this is a simple case. So we can pretty much do this one very straightforward. S plus 3 and s minus 1, and that one coefficient is A, B, C. So to determine A, B, C, and you can repeat the techniques we just done. So in this way, let me drop off the details and directly give us the number here. So that is 1, 8, 3, 4. Sorry. What I'm doing here, s plus 1 is 3, 4, and s plus 3 is minus 7. And s minus 1 is 1, 8. Okay. Good? So once we have done this one, then the remaining will be very straightforward. So therefore, the time response will simply is the inverse Laplace of the individual term here. Okay, so for the first term, the coefficient is 3/4, and 1 over s plus 1, and that corresponding is e minus t. Okay, so for this one, you converting is e minus t and multiply with the coefficients. Okay. For the second term, that is e and s plus 3. That converted is corresponding is e minus 3t. And with the coefficient multiplied, so that is minus 7 divided by 8. Okay. The last term, is coefficient is 1/8, and s minus 1, and that corresponding is ET. Good. So that's the result. And by further looking into the result, and we can gain some kind of physical sense about the system response. And before I doing that kind of explanation to you, anyone can get some hint by simply looking at the patterns of the form here. This is the total response of the system, because the system is under the forced excitation and also under the initial conditions. Initial conditions contribute to transient solutions. The given force excitation contributes to the what we call the steady state response. The steady state response always eventually will follow the patterns of the form of the given force. That is this term. And the steady state response follows the patterns with a different magnitude. This magnitude has been modulated by something, by transfer functions of the system. If you remember the transfer function concept, this is the transfer function representation of the system. This is the input, which is the force. This is the output. If you remember, we have done quite a bit exercise on the system to calculate the system's magnitude in the frequency domain, right? That is a portion. We know the magnitude of the output is equal to the magnitude of the system multiplied with the magnitude of the input. For this case, I can tell you the input has a magnitude equal to 1, and the coming out the magnitude of output equal to 1/8, I can tell you the system have an equivalent, the magnitude about 1/8. And that is the concept about the system, and that is my job and to tell you this. Okay. And by simply doing calculations and without the practical applications, and those ones wouldn't be seen in other classes. And this is a very important concept. And I know for right now, everyone learns so much details about the calculation, and very likely in 1 or 2 weeks, if I wouldn't take you stay with me, then in 1 or 2 weeks, the detail will become very quickly, because that simply is our human beings' biological natures, right? That's called the short-term memory. But this should be the long-term memory I wish I can impose to you, even years. If you go to the industry also for some kind of career, this kind of the important concept, hopefully I can imprint into your brain for a long time. If, say, you still have a concept 1 or 2 years later about this one, I'll feel very happy I make good, successful, very good job in teaching. You good? So basically here is showing how we integrate the knowledge, the things together to see one thing. Okay. On the other side, the two terms, you can see that has in the combination of an exponent, and that is decaying. So eventually the two terms will disappear. Will converge to 0. When t become large, or I would say eventually, the magnitude contributed from the two terms will become 0. And become 0, and that term actually is a contribution from the initial conditions. Initial conditions will contribute to the transient solution. Transient solution for stable system, this system is stable. For stable systems, the transient solution eventually will be done. And that one we can see from here. Okay. Even I can tell you this is an exponent with the -1 root, and this corresponding is -3, right? I can tell you the characteristic equation, it had a root -1 and -3. That one I can tell from the number here. Be good? And that is the way we learn to solve for the characteristic equations, and that is we call the characteristic roots. The characteristic roots basically play a role in controlling how how quick or how slow the transient solution will be decaying. And that is the way we coming from here. And for the transfer function concept, we wouldn't be able to see the transient, for the transfer function, we wouldn't be able to see this kind of transient response because in assumptions, the transfer functions model simply drop off the considerations of the initial conditions. So this one is only for steady state. Okay, so that's the way we build up the model for this. Okay, good. So that's it for this.